Hello, everyone, and welcome to today's free public webinar with TPC entitled, What is Three-Phase Electricity? We're going to learn all about that thing we hear all the time in the workplace, three-phase, and really what it actually means and how it actually functions. Today, our presenter today is our TPC instructor, our expert TPC instructor with decades of experience, Bob Kluke. He's been a master electrician. He's been in plants and all around the country doing things with three-phase. So no better to tell us all about it than Bob himself. Welcome to our session today, everyone. And as you're flowing in, I would like to remind everyone today just a couple of little housekeeping items before we get started. The first one being that this session today is being recorded, and this recording of the session will be made available on our TPC website within about 2 business days of today's session. Also, I wanted to let everyone know that at the same time as the recording being made available, the PDF of these slides will be downloadable as well at the same link on our website. You can go to live.tpctraining.com, go to the resources tab, and you can find all of our previous recorded webinars there as well on our main website. And then finally, 2 more things. One quick thing is that this is a public informational session, a 1-hour little burst of technical training, but it is not official training to the point where you're going to get a certificate of completion or any CEUs for that matter. But if you want to follow up this session with an official 1 or 2 day training course, that's where you can really get some of your official certificates of completion for that, just to let everyone know that. And finally, this session is live today. So we really want to utilize the live nature of this session for you to answer and ask questions of our instructor, of Bob, during the session. So we'll present for the first maybe 35, 45 minutes of this session, and then we're going to leave the remainder of this hour we have together for questions and answers. So for those of you who are curious about the topic of three-phase, definitely feel free to answer or ask any questions in the Q&A line. So if you see along the bottom of your screen, you should see a few different buttons there, but the button I want you to address your attention to is Q&A. Try to avoid using the chat line if you can, and put any questions and comments you have for our instructor in the Q&A line, and we'll be able to prioritize them, and I'll be sure to pose those questions to our instructor at the end of the session. So feel free to use that Q&A box. Also, before we get started and I hand it over to Bob, we have one thing we'd like to interact with you all on right now, and that is a series of poll questions. So what you're going to see showing up on your screen are 3 questions we would like to ask you about, whoops, sorry, this is not the right poll. Let me go to the right one here. I'm going to relaunch a poll. I'm going to go to this poll. We were about to ask you about PLCs, but we're not going to ask you about PLCs today. There we go. This is the questions we'd like to ask you about this, and that is, which of the 3-phase voltage levels are in your facility? And you can check all that apply. Do you have 208, 120 volts? Do you have 480, 277 volts in your facility? Do you have higher voltage, 4160/2400 volts in your facility, or you're not sure, or maybe none of the above? Pre-quiz question. So this is kind of a little knowledge check question. Feel free, no judgment. What are the units that we use for the total power developed by a generator of 3-phase electrical power? Let's say a diesel power generator, for instance. Is it kVA? Is it kVAR, kW, or you're not sure? And then finally, our third question is, do you know personally how to check whether your 3-phase system is what we call balanced? Yes, you do know how to do that. No, you definitely don't know how to do that, or you're not sure whether you know how to do that. We're seeing some great questions come in. And I'll give you just a few more moments to register your responses. Okay, good. It's looking like our answers are starting to even out. So I'm going to go ahead and end the poll. And then I'm going to share the results out with the world here. So you should see the bar graph of some of the results here. definitely the lion's share of you, 87% of you have 480, 277 volts of three phase. Now, what is 480 versus 277? We're going to talk about that a little bit today. But yeah, that is the predominant industrial voltage at the table here during this session. And also 69% of you here also have 208, 120 volts at your facility, which is more the commercial level voltage. Great. Pre-quiz question. So most of you have answered KW, 47% of you, followed by 29% of you say KVA. I will not spoil the correct answer until Bob gets a chance to let us know a little bit more about that. And then finally, the most popular answer here, how do you know how to check, or sorry, do you know how to check whether your three-phase system is balanced? Most of you said no. 49% of you, about half of you said no. You're not sure how to check whether it's balanced. So that is a great opportunity to get a little bit of know-how and knowledge and skills to the table on three-phase. So I'm going to go ahead and stop sharing these results. They should disappear from your screen, but if not, feel free to just click behind so you can see our presentation, which says, what is three-phase electricity? And without further ado, I'll hand it over to Bob to let us know a little bit more about three-phase. Thank you so much for being here, Bob.
Oh, thank you, Ryan. Thank you for the introduction and having the poll questions ready. That's excellent. I'd like to also thank everybody for attending this webinar today. So Ryan has done a good job setting these up every month, and this one happens to be on three-phase electricity. So before we can really get a good handle on three-phase, I do have to explain just a little bit how electricity is even generated at all with alternating current. So this is what I'm going to look at first, right? So we're going to imagine that over here, I happen to have a generator. And in that generator, I have put some magnetic lines of flux. Whether they're a permanent magnet or an electromagnet, really, that is of no concern to us. All we need to know is this, is that we have these magnetic lines of flux. And this is what is going to produce the electricity for us. So let's say that the generator is right here and it's not even turning at all, right? But I have a conductor in this generator and it starts right here. Well, to understand where that conductor might be over here, it's right here at 0 right now. So that's where my conductor is. As my conductor moves around this circle, you can see it's going to interact with more magnetic lines of flux. And as it does, it produces more and more electricity for us until it gets to the 90-degree position. And that's what we call, we're at the peak of this sine wave. And so it continues and comes right over to about 180 degrees, which would mean that we're right here now. So my generator has completed 1/2 of a revolution. And so it's gone right up here and come right around to right there. And you can see that at different points of this journey that my conductor is traveling, it interacts with more and more and more lines of magnetic field. And when it does, it gives us more electricity. And so at the 180-degree mark, that's great. We've come across in sort of a position that's above this line, but we have to complete our 360-degree journey. And so we're going to now come in the other direction, which is down here. And when we do that, again, we're interacting with magnetic lines of flux, but they are in a different direction. And so this is alternating current. We put only one winding inside this single phase generator, and one winding gives us one sine wave. And so on a single phase generator, we just have the one opportunity to interact with these magnetic lines of flux. And when we do that, we get this one sine wave. And we get either 60 of these if we are here in the US, or other parts of the world, you might get 50 of these every second. And so that's just a little bit about single phase. And we had to start with single phase so that we had a little bit of an idea how electricity is generated at all. And so we want to talk about that. And here we can see one gentleman enjoying his day, and he's making his canoe move. And so that's my single phase right there. And of course, we would utilize that in a lot of residential applications or small commercial buildings. So definitely, I could make something happen with this canoe, right? If I started paddling, I could move the canoe, and but we only have one person paddling, so I'd like to have you remember that a little bit. And like I said, mostly residential or small business, and not used in industrial applications very often, but it is adequate to run up to a 5 horsepower motor. But here's what we have to remember about single phase is that it does draw more current than equivalent three-phase motor would. And so that means we're going to have larger size equipment. We're going to have larger size conductors and not as efficient. So if we could get three-phase to come into a facility or generate it ourselves, then that would definitely be a big advantage for us. And so now we're going to take a little bit of look at three phase. And so now what did I do? I took that circle that we started with on our first slide, the 360 degrees, and just divided it by three and put three magnetic lines of flux inside that circle. And so they're going to be separated by 120 degrees. So we're going to evenly separate those out, right? But now, as my conductor uh, starts on its journey around these three separate magnetic lines of flux, I am going to be able to create three sine waves. And so now I would have what we call phase A, phase B, and phase C. And one big advantage of this is that this is also going to occur in one revolution of my generator. So in one revolution, instead of just having one sine wave coming out, I'm going to have these three sine waves coming out. And in any particular time, we can see that if one of my phases happens to be at zero, like phase A right here is at zero, right where I drew that line, well, phase B is three-quarters of the way up to its peak. And so this means that unlike single phase, where we might be at zero a couple times during that one revolution, with three phase, if one sine wave is at zero, the other sine wave is not. So my equipment really is never going to experience 0 volts because one of the other phases is always going to be increased. So we can see that here with my little generator, still using magnetic lines of flux, because we do need three things to accomplish generation. We need a magnetic field, and we need a conductor, and we need movement. And so those three things. And with that, well, of course, we can produce these three sine waves. Or if I only put in one magnetic line, then I would only get my one sine wave, which would be single phase. One way we can always take a look at this is if we have three transformers outside. And so those three transformers would deliver three phase into my facility. And so the utility is always generating three phase, and all we have to do is get it into our facility. That's it. And so one way to determine that is if the transformers are up on a utility pole, we could take a look and we would know immediately, right, if we had a single or three phase. All right, so now we can see the canoe, and there's no question about it that with the three people in the canoe, I'm going to be able to accomplish more, right? I am going to be able to easily get across the water. Here it is showing three paddles in the water at the same time, but I would have liked to seen one paddle in the water and then one maybe paddle up here and the other paddle getting ready to come in the water and make it so that they were separated out a little bit, like my sine wave. But my big point on this slide is this, Instead of just having one person do all the work, we now have three people sharing the work. And so that's going to make it much more efficient for me to utilize this electricity. Just no question about it. So three phase, very common in large buildings, been around for a very long time, right? And we're going to see in a little while who the uh, let's say, inventor or discoverer of this was. But large industry definitely going to use it all over the world. And in today's world, we are so dependent on data that data centers are popping up everywhere. In fact, I was in Chicago not that long ago teaching at a data center, and that one data center was the largest user of electricity in the city of Chicago. So these things are really hungry for power. And, uh, and we're going to give it three phase because that is going to give it more power than we would just for single phase. And so uh, the third bullet here says it's kind of expensive to convert from an existing single phase installation to a three phase installation. But I want to give you an idea if we have just like one piece of equipment. So let's say this that we have a small manufacturing facility somewhere and they're on single phase. And so all they have is just single phase in there, but they got a good deal on a three phase piece of equipment. And so they only have one piece of three phase equipment, right? Well, very economically, what we can do is we can purchase a VFD. And that VFD, we can bring single phase into the variable frequency drive, and it will give us three phase out. And it does that with electronics. And so we're not going to be using a magnetic field for that. The magnetic field will already have been produced by the utility. And all we're going to do is just bring single phase into my drive instead of three phase. So this particular drive gives us a choice. And when I bring in the single phase on the back end of the drive, it will deliver three phase to that piece of equipment. And that's very economical to do that. Plus, you get speed control. So, a lot of times, if we only have one piece of equipment and we don't want to convert our whole single phase system to a three phase system, we could pick up a fairly economical VFD and definitely have three phase on the load side of that drive. Also, this slide is going to give us an idea, a little bit of history and where this all came about. So we do see the name of Nikola Tesla here. And so Nikola Tesla had the patent for the three phase transformer, for the three phase generator, and for the three phase motor. And he sold those three patents to George Westinghouse. And George Westinghouse really wanted to distribute that throughout the whole United States. And so he did hire Nikola Tesla. They did go to Niagara Falls and they put in Tesla's three phase generation system in Niagara Falls. And so uh, Tesla was the first person to be able to understand that, especially on a three phase motor, that we would have a rotating magnetic field inside there and allow those three phases to give us some mechanical power at the end of this shaft right out here. And so they had to make some decisions back then, right? They had to make a decision on frequency. So they did, and they decided that 60 hertz was the way for us to go. And what we should understand is the Germans were doing the exact same thing at the exact same time. And the Germans decided that 50 hertz was better for them. And it ended up in a dead heat. And so we stayed with our 60 and they stayed with their 50. And that's probably the way it's going to be for a while. But with the three phases, we could definitely provide electricity to a variety of customers. And during that time, we wanted to transmit this as long a distance as possible. It wouldn't be nice to be able to go from Niagara Falls all the way to Miami. And to do that, we definitely had to increase the pressure. So sometimes we would get these transmission lines, you can see up to 138,000 volts, just so that we had enough pressure to push that electricity to wherever we wanted it, to eventually our um, uh, industrial customers and even our residential customers. So this all started with Nikola Tesla. He had a dream as a young boy, 9 years old, that he was going to put generators in Niagara Falls. And he was able to accomplish that with some money from George Westinghouse. But it was his expertise and his three patents that really allow us to be able to have our distribution system that we know today. And so that's important for us to remember. In the poll that we conducted earlier that Ryan distributed to you people, you said that 480-277 was everywhere in your facility, right? And so this is exactly what we would have. We would have three transformers outside your facility somewhere, either hanging on a pole or they could be inside an enclosure. So if they were inside of an enclosure, there would still be three transformers here, but you would only see one enclosure. So you would have to know what the system was, if it was three phase or single phase. Because when you look at it, oh, there's only one enclosure there. It must be single phase. No, because sometimes we put three transformers inside that one enclosure. And in this particular case, we have connected the transformers in what we call a Y configuration because it looks like the letter Y, right? So that's why we did that. And when these three energized conductors come into your facility, phase A, phase B, and phase C, we're going to bring them into some kind of distribution equipment. But eventually, right, they're going to get into a panel somewhere. And we're either going to have a main breaker in that panel or we're going to have uh, main lugs only. But there's going to be three lugs that we're going to terminate in phase A, phase B, phase C. And they would come directly into that panel. And so we'd be bringing in uh, three phase, 480 volts, no doubt about it. When we establish our connection to ground, which we're going to do that through a grounding electrode conductor connected to some grounding electrodes, usually a metal water pipe, building steel, the rebar in the concrete, or even something a little bit more familiar, maybe ground rods. When we do that, we establish what we call a neutral. And so we're actually going to be bringing four wires into the facility, three energized conductors and a neutral, and the neutral is connected to our grounding electrode system. And so when we do that, right, we might have out here a three-phase motor somewhere. All right, so if we have that three-phase motor, that is not going to need a neutral. And so we would just bring phase A, phase B, phase C to that three-phase motor, and our motor would turn. No question about it. But we might want to pull some single phase loads off this. And to pull a single phase load off, all I have to do is get one energized phase and my neutral. In this case, you can see that when we go from any phase to the neutral, we get 277 volts. So we use that a lot for industrial and commercial lighting. And we'll pull our lighting off of that system. And so a couple things I do want to mention about that is that if I did have that three-phase motor and I did not need my neutral, I'd be using a three-pole breaker. And I would put in phase A, phase B, phase C off that three-pole breaker. If I wanted some single-phase lighting, no problem. Put in a single-pole breaker and come off any phase with an energized conductor and then my neutral, and I would get my 277. So some important things to think about here. One is the color code is kind of important. So as long as we have wired in accordance with how we've installed this over history, and so time has evolved us to the point where This is the color code widely accepted for three-phase here in the United States, and it was for a long time brown, orange, yellow. That would signify 480 volts. And so in the National Electrical Code in 110.15, they have now utilized the orange color for something a little bit different, which is going to be a high leg delta, which I'll explain in a second. But now you might see purple out there, but a lot of people are still using brown, orange, yellow. So that's no problem. But they should identify that and let us know that those colors mean uh, three phase 480. Also, if we're going to test this, you can see if we go between any of these phases, if we go to the outside of this transformer configuration, anywhere between brown and orange or orange and yellow, we're going to get 480 volts. If we go from any energized conductor to our neutral, we would get 277 volts. And you want to be very careful. This is not a voltage that we should take lightly. For instance, if we're working on those lighting circuits and they are 277 volts and they utilized all three phases, in other words, my first room is on phase A, my second room might be on phase B, and my third room on phase C, and we are doing a light somewhere, that neutral could be shared by all three phases. And when we're trying to work on this light, no matter what it is, we want to make sure we lock and tag out all three phases because I am going to tell you right now, 277 volts hurts, and it's not a good voltage to try to mess with a whole lot. We could also have this system, which is very similar, only just a little bit lower voltage, right? So on this one is going to be 120, and so let's say this, that the utility comes in with 480, and that's all they're going to give us, 480, 277. So somewhere in my facility, I would have a transformer to change that down to my 120, 208. But this works very similar as the other system does because from my energized conductors on the outside, I am always going to have the higher voltage, which in this case would be 208. So if I went from black to red, I'd get 208. If I went from red to blue, I would get 208. So always on the outside of the system, we get the higher voltage. If we go from the outside to our neutral, we're going to get that lower voltage, which in this case is 120. So usually we have both systems in our facility, right? 480, 277, which we utilize the 480 for large motors, the 277 for our lighting. Here we could use the 208 maybe for some smaller motors, and then we use the 120 for our receptacles. So usually we have all four systems in a large facility, and sometimes in a smaller facility, we would only have this system. But definitely we would have three phase with either one of these systems. And so then this system is not quite as common anymore. And so this is what they call a high leg delta. And I wanted to show you this because it is three transformers again. So there's no doubt about it that I do have a three phase system here. But we configured the transformers not in a Y, but in a triangular configuration. And we call that a delta. And this delta is not one to take lightly either, because notice it says high leg. And so, just like my other system, if I come from the outside of my energized conductors, phase A, phase B, phase C, then I could definitely have three phase 240 in this system, and very handy back in the 1950s because I could run three phase motors on 240 volts, no problem, and also have available to me 120 volts for receptacles. So it was pretty darn handy, right? But the issue is, you're going to see it here in a second, that when I did want that 120 volts, I had to be very careful about which phases I would use to get my 120 volts. On phase A to my neutral, no problem. That would be 120 volts. That would be no issue whatsoever. Phase C to my neutral, again, no problem, 120 volts. But here's the one that's a little off a little bit. It would be phase B to my neutral, and that would be at 208 volts. So if you ever look into an electrical panel and it's three phase, and you see every third breaker is missing, and it's taking single phase loads off that panel, and every third breaker is missing, put that in the back of your mind, because somebody who was very familiar with this system knew that they better stay away from that high leg. Probably not a good idea to plug my 120 volt equipment into 208. So they had a lot of experience with it, and they could stay away from that system, no problem whatsoever. So there's other types of deltas that we could also utilize. We have corner grounded deltas, we have ungrounded deltas. Those are for certain applications, but the majority of our three phase is going to be in a Y configuration. That's where the majority of it would lie. But there's still some of these out there. And so I wanted to make sure I did show you that for sure. Also wanted to talk just a little bit about some of the ways that we can calculate three phase. And so DC, you can see right here, some pretty simple formulas. You know, uh, just looks like we're going, kilowatts times 1,000 divided by voltage. I mean, no problem. The minute we get into single phase, though, we have to look at power factor. And I'm going to explain power factor coming up shortly. But let's jump over here to three phase. The minute that we get into three phase, I still have to look at what power factor is, but I have to include 1.73. And why do I have to include 1.73? Because remember our three phases. Our three phases are not embedded right on top of each other. In other words, they do not all reach the peak at the same time. If they did, we could get rid of the 1.73 and just put 3 in there. But our three phases are separated by 120 degrees. And so now we have to use vectors to determine how much energy is going to be used. And those vectors are going to be separated, like I said, by 120 degrees. And when we do that, the square root of 3 comes into play. And for a long time, Nikola Tesla struggled with this, why he was only getting 1.73 times as much. But it's all because of the 120 degree separation that we have. So anytime we do a three phase calculation, we have to utilize 1.73, the square root of 3, plus the power factor. Okay, so you can see here three types of power in these AC circuits. And Ryan had a poll question earlier. How much power does that generator have to supply? Well, here it is. The generator has to supply what we call apparent power, or kVA. All right. So that is going to include our reactive power. That's the power that we lose to energize our magnetic fields or charge our capacitors. That power just sort of goes back and forth in the line. That's it. And the utility is really not charging us for that power unless our power factor gets so out of line that they will charge us a penalty for that. And then we have our true power, which is the actual amount of power that's actually doing work. And so whether this is a generator or it's a transformer or a photovoltaic system, you name the power source, it's got to supply everything, because we're going to lose some because of the magnetic fields that we have inside of our motors, all of our coils, and charging all of our capacitors. So we're going to lose a little bit of that power, right? And I want to say that the best way to explain that is something that a lot of people can relate to, right? Is that we've got somewhere a keg of beer, and we ask the server if that we might want to have a keg of beer to go. A glass of beer to go with our dinner, and so that's fine. Well, the keg has to produce all of this. But you can see from here up, that's not going to do much for us, that foam. And so the foam is just taking up space, basically. But the keg had to produce it, and that's it. But what's actually going to have an impact on us is the liquid part of it, right? So that would be compared to the KW. And so the KVA is everything that the keg produced. But our coils and capacitors would be reflected by the foam on top here. So no matter what our source is, it has to produce enough power so that we can charge our capacitors, energize our coils, and make motors turn. But some of that is going to be just surging back and forth in the line, not something that actually is utilizing the power for actual work. So that's how I kind of like to explain that one a little bit. We'll do a three-phase calculation so you can actually see it. This is going to be for a motor. And we do have to explain that the power factor is just how we're utilizing that electricity. And so for a motor, what would happen is the voltage sine wave would start first, and then a little bit later, we might have that current sine wave. If they both traveled in unison or unity, then they would hit their peak at the same times, but they don't because a motor has a coil inside, and it's very difficult for that current to get through that coil. So it lags a little bit, and they put right on the nameplate what the power factor is. So already we're not utilizing all the electricity because of the power factor. But we also have to know the voltage that we're going to be using, which in this case would be the higher voltage, and how many amps we're going to use, which in this case would be the lower amps. When volts goes up, amps comes down. And so now that we know that we're going to be using 460, point 0.9, and 83, the only number we have to include with this would be our 1.73. And we can calculate how much it would cost to run this motor, which is a large motor. It is a 75 horsepower motor. So this motor is going to weigh close to a little over 1,500 pounds. So we know it is a large motor. Let's see how much it would cost to run that motor for a month. And so what do we have to do? We're going to use this formula, our amps times our volts. We got to get 1.73 in there because it is three phase, and then our power factor. So we got the lower amps because we are using the higher voltage. We put in 1.73, the square root of 3, because it is three phase, and then 0.9. So that gives us this many watts. All right, that's great. But we're going to divide it by 1,000 because the utility likes to charge us in kilowatts. Kilowatts per, uh, um, you know, per hour. They're going to charge us for that. So if that motor runs 24 hours a day, let's say it's a month that has 30 days in it, that's 720 hours a month. All right. So 720 times our 59, which is our KW, gives us this many kilowatts per hour per month. And if the utility is kind to us and they're only charging us 10 cents per kilowatt hour, it's going to cost us over $4,000 a month to run that 75 horsepower motor. So that's a little calculation using three phase. So the advantages of three phase. And then after this, we are going to open it up to questions, just so you know. So some advantages, right? It's going to deliver more current. And so we're going to have three sine waves instead of just one. And that current is going to allow us to do more work. And so three phase power. And it's how much more is it going to deliver? It's going to deliver 1.73 times as much more. So we should understand that because of the 120 degrees separation. So we're going to get more power out of three phase, right? That's one great thing. Also, we can transmit more of this. Our conductor can be smaller in size than it would be if it was single phase, and we can transmit it over very long distances. So that's a big advantage for us, no doubt about it. Also, the size of our equipment is going to be reduced. And so because of the three sine waves and giving us more per revolution, we're definitely going to have our equipment be smaller in size. And so that's a great thing for us. And also, we see that these three-phase motors are very simple in construction. And so we can manufacture these three-phase motors. It's not going to cost us a lot of money once we mass produce these, unless, of course, we get up into the larger sizes of three-phase motors. But these also start themselves. And so they just can get more power. We know 1.73 times as much and more efficient, no question about it. And we're not going to have any type of pulsating power like we might with single phase with just the one sine wave. And so with the three sine waves, our equipment is just going to run smoother, less noise, less vibration, because we're not hitting zero at all with three phase. One of our windings will always be up near the peak, and it's going to occupy less space. So if we talk to management, right, space is money, and no question about it. If I can put more machines in the same square footage area and make more product, I'm going to be more profitable. So three phase would definitely allow us to to make that. The three phase motors are going to have a better power factor than single phase, and so we're not going to waste as much electricity in that case. And so now we're going to open it back up to questions, and I am going to let Ryan take over from here.
Thank you so much for sharing your wisdom, Bob. And we're getting some great questions starting to come in the question and answer box. Feel free to use that Q&A box to ask your questions now if you have some curiosities about the topic that you'd like to know about. And we'll be able to spend, maybe 15 minutes or so tops on answering some of your questions. We're starting to get some good ones, Bob. And I think one common question curiosity we're seeing now is, I think there's two categories of this question, so I'll ask them both at the same time. We talked about the benefits of three phase just now. Specifically, why don't we have two phase is the first leg of the question. And why is there no such thing as two phase out there in the industry? And I know there's a really interesting interesting thing to think about with two phase. But then on kind of the other side of the coin, why not four, five, six, seven phase? Would you say the industry has landed on three in particular?
That's excellent. So that goes back to the early 1900s also. They did experiment with putting more windings inside those generators. And so they did experiment with six phase. We should always think of multiples of three, right? So 3, 6, 9 would always be the way to go because of the fact that we are turning in that 360 degrees, and we'd like to divide it up evenly if possible when we do that. But here's what they found, and very interesting, that when they discovered that three phase was better than single phase, then they started going to 6 and 9, but it was cost prohibitive, that they could accomplish just about the same type of distribution with three phases as they would just if they were going with 6 or 9. And so also their generators could be smaller. They wouldn't have to be as large. And it was just more cost efficient for them. And the motors, the three-phase motors were working just perfectly on that. And how come we don't have, like you said, two-phase? Well, two-phase was not used pretty much at all, because I want you to think about this, that if we only have one transformer and we have single phase, we do have two ends of that transformer. So we do have two energized conductors there. And so single phase really is going to give me two energized conductors, and then my neutral would be right in the middle. And so we can get 240 volt single phase, but it's really giving us two energized conductors. So instead of trying to come up with another winding inside that transformer, they said, no, we've really got two energized conductors here. we are taking care of a higher voltage with the one winding, and that pretty much steered them to the straight three phases. And the three phases have certainly served us well in the last over 100 years. So we're not going to have two phase because single phase pretty much takes care of that.
Excellent. Thank you so much. Another really good curiosity here on the Q&A line is kind of the difference in performance between the 480 277 we talked about, the brown, orange, yellow, versus the 208, the red, blue, black. Is there a difference in efficiency between the higher voltage versus the lower voltage version of three phase? Let's say we assume the same power factor.
So that's great. That's a great question. So immediately when we go to the higher voltage, we understand that our current is going to be smaller. And so with that, that's going to be um, smaller conductors. So we're going to have a little bit of savings, right, by buying a smaller conductor. But what really is going to help us here, this current generates heat, and heat is our enemy in the electrical world. So if we can keep our current lower, a lower flow, then it's going to produce less heat. When it produces less heat, it is going to allow our equipment to last longer, less problems using them. And so as far as the cost of let's say paying the utility, it's not going to be a big difference there as far as 208 or 480. But overall, it is going to be much better for us in the long run because it's going to be better on our equipment. It's going to make our equipment last longer. Our conductor sizes can be smaller, and it is going to the 480 is definitely going to allow us to sustain our equipment for a much longer period of time.
Excellent. And I think we had a couple questions now on this topic of switching the direction, the rotational direction of the motors. How is it that if we swap any two wires coming into that junction box of that motor, it reverses direction? How does that work?
So I like that. Okay, so first of all, we have our three phases, right? Phase A, B, and C. And first, I'd like to mention this, that the NEMA, the National Electrical Manufacturers Association, has a standard for what we're talking about. It is the MG2 standard. That's for motors and generators. And so you can switch any two phases and it would reverse that motor. There's no doubt about it. But the MG2 standard from NEMA, they would really like to encourage that we always switch the two outside phases. So phases A and C would be the two that we're going to use to reverse that three-phase motor. And the reason for that is if we always utilize the two outside phases, eventually our whole facility will be in phase. And we wouldn't have to worry about being out of phase. We'd always be in phase. But here's the reason why it does that, right? Is because we are separated by 120 degrees. And so we have an automatic phase shift to begin with of that 120 degrees. To get a motor to start to rotate, we need a phase shift. We need to get a difference between the north and the south polarity. And so what we have to think about here is, let's say that phase A right now, that the magnetic field associated with this, let's say right up here is north. But our next phase coming, the magnetic field could be on the opposite polarity. So down here, you can see that on B, maybe I'm down here now. So the minute that I swap these two, I'm going to be swapping a north and south pole. And what that's going to mean is in this case, we are going to spin in the opposite direction the minute that we switch the polarity of those phases. And so one, it might be in this direction, but the other is going to be in the opposite direction the minute that we reverse these over. So that's all it is. And that goes back to the Greeks where like forces will repel and unlike forces are going to attract? That was an excellent question.
Yeah, lots of great curiosities coming in. We're going to try to answer as many as we can in the next 10 minutes. But in the meantime, any of you who are still here, but curious about some of the terminology Bob is using here, particularly around grounding electrode conductors and ungrounded versus grounded, a single phase, three phase, the different standards for coloring and requirements versus standards. Um, you're probably talking about the National Electrical Code, right? And so you see here the NEC challenge. If you want to continue to quiz yourself, you see this link here. Go to Jade Learning, which is a TPC company, and get little updates on the NEC challenge if you like, as well as if you want to learn about solar power and browse the catalog. There's stuff online, resources, free resources we offer outside of these webinars for you to engage with. So be aware of that. We got two good questions here, Bob, on um, power factor. Let's say power factor starts going down and down and down, and the whole idea, the common standard idea of using capacitors to boost the power factor and kind of replenish it or make it better. How does that work? How do capacitor, let's say having a capacitor bank, help improve power factor?
Sure, great question. And so we use a little phrase that has some acronyms in it to explain this a little bit, and it's called Eli the Iceman. And so this is probably the best way to explain this. L stands for inductive loads, which let's say motors, and C stands for capacitive loads, wherever we might have capacitors, right? So first we'll talk about motor circuit and what happens in a motor circuit to our sine waves, because we actually have two sine waves. We have one sine wave for voltage, and we have another sine wave for current. And so when these two sine waves both reach their peak at the same time, we say they are at unity and the power factor is one. And that's what happens when we have, let's say, single phase resistive loads. So if we have a toaster in our home somewhere, both the voltage and the current sine wave would reach its peak at the same time. So that's good. But all of a sudden, we have a dryer that has a motor in it, right? And so inside that motor has some coils. Okay, so in a motor circuit or an inductive circuit, the voltage sine wave, it can make its way through those coils just as if the coils were not there at all. But the coils have a changing magnetic field that is associated with this sine wave. The changing magnetic field inside here is going to get large and then small, just like the sine wave gets large and small. So imagine imaginary magnetic lines of flux being large and small. Well, that inhibits our current, and our current cannot make it through here as fast as our voltage does. So the voltage makes it through, no problem. A little while later, here comes the current. And so now, because they are not traveling in time anymore, we say that that's out of phase. And depending on how far it's out of phase, we give a number to it. Let's say zero 0.9 power factor. So they'd be 10% out of phase, let's say. But then you have a capacitive circuit that works just the opposite. In a capacitive circuit, if we have capacitors around, then the current will go through there like nothing. Man, the current is not going to be slowed down a bit. A little while later, here comes the voltage. So, if that's the case, right, and we have a lot of motors in our facility, and our power factor is getting real low, maybe down to zero 0.8, we can put in some what we call corrective capacitors, and when we do that, it brings these two sine waves closer to unity or one. And so by putting the capacitors in the circuit at, wherever, sometimes we put them in right at the very beginning. Sometimes they're outside the building. Sometimes they're at our switchgear, but they will bring those two sine waves back together if we do have a motor load that is making them have a low power factor. That was another very good question.
Thank you, Bob. Uh, Here's another great question I really like that has a lot to unpack in a very brief question. And I'll let you address it how you please there, Bob. And that is, why is there no quote unquote common wire in a three-phase system?
Okay. So I want to say it depends on our system, right?
Right.
And so if I have a Y system, all right, and that Y system, we have connected the midpoint of this, the common point. So this is the common point. We are in a Y system now. I connected it to my grounding electrode system. This is my grounding electrode conductor. This is a common point, and this would be our neutral conductor or our white or our gray wire. So in this system, there is a common point in this three-phase system right here. No question about it. Let me give you a system where there is not a common point. And so that would be a system that looks like this. It's going to be a delta. So it's going to look a little bit like a triangle. And I'm going to say that I'm going to ground this corner. And I'm going to bring in phase A, phase B, and phase C. Here, I have no common point. I didn't tie all three transformers to the same point. And so there is no common. I just have my three phases. So what can I run off this kind of a system? Three-phase loads. So I'm going to run three-phase loads, three-phase motors, but I cannot run single-phase loads off this system. So sometimes we do have a common point. Our Y systems do have a common point, but some of our delta systems do not. So that's the differentiation in that.
Great call. Just a brief, maybe a topic on the whole idea of troubleshooting in three phase. What can cause one of these three phases to drop out, and what happens when they do?
Great question. So, a lot of different reasons, right, that we could go to single phasing. And so, um, and by what we mean is if the utility is giving us all three phases, and then we start to single phase, it means we lost a phase somewhere. And so there could be an open connection at the utility. And so the utility could have an issue, right? Or our equipment could have failed. Maybe our switchgear has an issue inside. Or we could just have a loose connection somewhere and we lost one of those three phases. But I can tell you our switchgear should have protection for that. When we do lose a phase from the utility, our switchgear has protection inside that is going to de-energize to make sure that the rest of our equipment in there is not going to fail. We don't want to burn something out because we started to single phase. So our switchgear will have protection for us if that does occur. Uh, Anywhere near the switchgear, line side or load side. We lose a phase, and we would definitely have some protection from our switchgear. But if that phase is lost way downstream somewhere, then we could have a motor go into single phasing. Uh, we better be concerned there about a lot of extra heat, and it could impact my insulation on my stator windings, and we could end up with some ground faults there. But if it's up near the switchgear, we definitely got some protection for that. So that is one good thing for us.
Absolutely. I always love the really interesting, not what you would expect type of conversation of, okay, we had three phases. You lose a phase, how many phases are left? And the answer is one, right? And not two, but one, because of um,
Single phase with
yeah,
single
it's a
phasing.
single phase left over. So that's another interesting thing about the whole two phase debate. Um, if there's just one delivering and one returning, that's a single phase left over. So definitely got a lot of curiosities from the crowd here. We unfortunately have to leave it there in the interest of everyone's hour-long time together. Thank you so much for being here. And for those of you with additional great questions about how VFDs turn single phase to three phase, how to do more about the balancing we talked about in today's poll, the 240 volts being used in both three phase and single phase applications, all those really great applications. Someone's installing an HVAC system in their facility, and a couple other great curiosities. Uh, get a chance to sit in the classroom or on Zoom with one of our instructors and spend those 2 days really getting those questions answered. It's a really great hands-on way to learn from people like Bob in the classroom environment. Email us, give us a phone call, watch back some of our webinars on our main page. Again, go to tpctraining.com. There's a bunch of great stuff for you to check out there. And definitely let us know if you have questions. Give us a call and we're happy to help set you up with what you need. So thank you again, everyone, for being here, and have a great day.